Okay guys, let's take a look at today's lesson. What we're going to do is we're going to be looking at some calculus topics that apply to polynomials and rationals. That's the unit that we're in, the polynomial and rational unit. So we're going to look at some ways we use calculus with those kinds of functions. Really two different goals today. One is to look at limits to infinity. And that's probably our most complex goal, is to work with limits to infinity. Our second goal is to look at these are formulas that for integration that you will learn next year. We're not going to integrate. We're just going to try to get what you're given to look like this. That's all. That's the second lesson. It's pretty straightforward, I think. As with the A's and the U's, let's just talk about them just a little briefly. We're going to be needing to know what A and U is. A is going to be the constant and U is the variable in this expression. So that just keep in mind, because they both look like variables to us, like which one is which. Just need you to understand A is the number and U is the variable. And so I just wrote that down here so that we would be sure we understood what that was. Okay, so those are what we're looking at. So let's look at limits to infinity. This first part is basically just how would you read this statement. You know, the limit of f of x as x approaches negative infinity is L1. Maybe it's 2 or something, or negative 5. It's a number. That's just how we would read it. And hopefully you recall our work with limits last semester, what a limit is. Basically, in the simplest form, the answer to a limit is the y value of the function at this x value. I mean, that's the simplest explanation of a limit. It's the y value. It's the y value of wherever x value we're going. This is a little different because we're going to positive and negative infinity. Okay, so that's a little bit different. And for this purpose, we're going to use a special limit. And the special limit, I'm going to circle them, would be something that you would memorize. Not that you're going to have to recite the limit, but you're going to have to use it. You're going to have to use the limit in what we're working this lesson that we're working on. Okay, that you just have to use it. So let's talk about what that means. So in this case, if let's say n is it's a number and it's getting bigger and bigger. So maybe it's 1, then it's 5, then it's 25. So excuse me, this x is getting bigger and bigger. 1, 25, so forth, just large, getting, a million to some power. And the power n, it could be any power, 1, 2, 3, 4, whatever positive power. As this denominator grows without bound and the numerator stays stationary, it doesn't have to be a 1 actually. It could be any number. It could actually even be like a million. It doesn't matter. As long as it doesn't move, the bottom is going to continue to get larger and larger forever. Right? Infinity is like a forever. It just keeps growing and growing. So if you imagine that scenario, if the numerator doesn't move and the denominator continues to get bigger and bigger and bigger, this entire fraction's value is going to get smaller and smaller and smaller. Right? And what it's going to do is it's going to tend, T-E-N-D, it's just kind of a formal way, it's going to tend to 0. So this limit is going to equal 0. It's going to go towards 0 because this fraction is going to get so small that we're going to say it equals 0. Now, in this particular instance, this is if going to negative infinity, this is if x is negative. If x is smaller than 0, we use this. We don't use this one that often. This is the main one that we're going to be using. Okay. Then we have the definition of a horizontal asymptote. We talked just a few days ago about the Precal way to determine horizontal asymptotes. Remember that, where we found the highest power and then we divided the coefficients? Well, there's a calculus way to find horizontal asymptotes, which I was explaining, a few days ago, and this is the calculus way. You would take the limit as x goes to infinity or negative infinity to find your horizontal asymptote. That's what you would do. Okay? And that's what we'll be working on, is finding limits to infinity. So these, I'll just talk about this just a little bit. These are, we could just say templates. These are like little formulas that you'll be using next year. And we'll have, these are integrals. We don't really need to understand a whole lot about integrals right now. I'll just tell you an integral in the simplest manner finds the area under the curve of whatever this function is. That's the simplest explanation for it. You don't need to know that. That's what we'll be doing. And if it's in this form, we need to make something look like this. And I just have a few examples on the other page where we have something that almost looks like this, and we just rewrite it so it looks like this. This is just a practice on rewriting things to look like the formula. That's all. You're not going to do anything with it once you've rewritten it. You're just going to rewrite it. Just practice on the algebraic portion. Okay, so any questions before we do some examples? Okay, let's go to our example page. We have a few limits. So we will be working towards different techniques to do limits to infinity. Okay, but we're just starting out, and as we start out, I want us all to do it the same way. Okay, we're going to do it the algebraic way. Later on, as you become more familiar with limits and you do more work, there'll be other techniques that you can use. But for now, we're just going to do them all the same way. We're going to do them algebraically. And what we want to do actually is we want to get a bunch of those little baby limits. You know, the limit as x goes to infinity of 1 over x. We want to get a bunch of those little fractions so we can get rid of them. That's how we're going to use that special limit, is we're going to try to turn everything into little tiny fractions that we can get rid of. Okay, because it's going to tend to 0. So the algebraic technique that we use is we multiply this expression, these are for rationals, by 1 over the biggest exponent. And so we look, the biggest exponent is x squared, so I'm going to multiply by 1 over x squared over 1 over x squared. So this is the algebraic technique to solve this limit to infinity. So now I'm going to distribute that, and I'm actually going to write this next step out. Normally I distribute and simplify at the same time, but I don't want anyone to be confused exactly what I'm doing. So I'm actually going to just straight multiply it out. So this is the limit as x goes to negative infinity of negative 2x squared over x squared plus 3 over x squared all over 3x squared over x squared plus 1 over x squared. Okay, that's really what we're doing. We're multiplying it all out. Once we multiply it all out, we're going to simplify it. We're going to simplify. And so this step I normally don't do. I normally go straight to the simplification step. And if you get comfortable with it, you can do the same as well. I'm going to go straight to simplifying. So I'll just kind of out of room, we'll go up here. So the limit as x goes to negative infinity. So let's see, I have negative 2x squared over x squared, which is negative 2. 3 plus 3 over x squared over 3x squared over x squared is 3 plus 1 over x squared. Okay, that's usually would be my second step. Okay, is everybody okay? So now I try to find all those little fraction little guys, because I am able to, limits are so nice. I can actually take the limit of each one of these things individually. I can take them individually. And so I'm going to look at these things one at a time individually. And this little fraction right here, that's going to tend to 0, right? Because I have a number over something that's getting bigger and bigger and bigger. And this little fraction is going to tend to 0. So I usually circle them. I circle them because that kind of tells me, okay, that's going to go to 0. I don't need to worry about it. That's going to go to 0. I don't need to worry about it. Now I'm going to take the limits. I'm going to consider if I put negative infinity, you know, think about going to negative infinity. These will 0 out, and I will be left with negative 2/3. And that's my answer to that limit, doing it the algebraic way. Okay. We okay? Okay, let's look at a little bit different one. This b, we're going to do the same thing, use this algebraically. So I look for the highest power, that's x cubed. So I'm going to multiply by 1 over x cubed over 1 over x cubed. Now this time, hopefully it's not too upsetting. I'm going to multiply and simplify at the same time. Okay, so I'm going to actually skip this multiplication step and go straight into simplification. So we have the limit as x goes to negative infinity. So let's see, I multiply negative 2x cubed, so I get a negative 2 plus 3 over x cubed all over. Let's see, we get 3 over x plus 1 over x cubed. Okay, so I multiplied and simplified at the same time. Okay, so let's identify our little fractions that are going to tend to 0. So this little fraction is going to tend to 0, and this little guy is, and this little guy is. Okay, that leaves me with just a little bit of a problem, because that means it's like undefined. Now, with limits, when we get a number over 0, that does not mean that the answer is undefined. That means that the answer is either positive or negative infinity. We don't know. We've got to look at it. Okay, I don't remember. I think we've talked about that before. So if it's a number over 0, we're kind of done, and it's going to be positive or negative infinity. If it were 0 over 0, which we're not going to be dealing with here, with infinities, we don't have the 0 over 0, or at least I don't have any in this lesson. That's the indeterminate form, right? That means we have to do something. But here, if it's a number over 0, we've just got to figure out which way is it going. Is my answer positive or negative infinity? That's what I need to know. And to do that, the easiest way to do that is to go back to the original expression, and we're going to think about it. We're not going to write anything down. We're going to think about it. We're going to think about what would happen if I put a really large negative number down here in the denominator. What would the sign of the number be? The denominator is going to be positive, right? And we're just thinking through this. We're thinking through. If I were to put a really big negative number in the numerator, this x portion would be negative, but what would happen? It would have to multiply by the negative 2, right? So this is going to turn positive. So basically, the larger number I put in, or all the large numbers I put in, are going to be bigger and bigger positive numbers, because this negative times negative is a positive. So this is going to tend to infinity. That's what we would write. That would tend to infinity. Okay, we okay with that? So that's like a thinking problem to figure out which way it's going, positive or negative infinity. But the important thing is to know when you end up with something that looks like that, that's not the answer. The answer is positive or negative infinity. You need to figure out which one. And if you just want to guess, flip a coin, 50-50. I mean, if you're living dangerously, I don't know, flip, just eeny, meeny, miny, mo, right? But it's going to be positive or negative infinity. When we have a scenario like this, we're going to infinity. Because let's just talk about exactly what's happening. This is a rational equation. We graph those, right? They don't just stop as they head out as x gets larger and larger and y gets larger. They don't just stop anywhere, right? They don't become undefined. They are either going to go, in this case, they're either going to go, as we're headed to, we're headed this way, we're going that way. The curve, this rational, is either going to go like this or like that, right? It's going to go one of the other ways, and according to this information, it's going to get larger and larger. It's going to go up. Okay, you can even graph it to figure out if it's positive or negative infinity. You with me? So it's a thing. It's not just, oh, I get to stop. It's undefined. That's not how it works. Okay? So the last kind, I think, is the most complex kind. So I kind of walked us in, right? This is a pretty straightforward one. This is one where we got to figure out it's positive or negative infinity. This one is a bit more complex because it has a radical. And so let's look at this. We're still going to do this algebraically. And in the denominator, the largest power is 1. And in the numerator, now we all know that we're not allowed to split that radical into little pieces. I think we all understand that. But if we just kind of think about it, if I were to take the square root of x squared, I would get a power of 1, right? I would. And so really 1 is my highest power. Now, this brings us to the time where we need to talk about the square root of x squared. Now this is a side note. Okay, this is a side note. The square root of x squared. The square root of x squared actually simplifies to be absolute value of x. You may not have heard that before, because in the lower maths it's not that big of a deal. And they just make it x. But it is a big deal. This, if I were to write the square root of x squared equals x, that is only true when x is positive. Okay, I want you to think with me. Let's say x is negative 2. If I were to use this equation, and I were to put a negative 2 in for this x, and a negative 2 in for this x, because x is negative 2, I would get a statement that's not true. Right, you with me? I would get a positive equals a negative. That's not true. That's why this is the actual answer. We went over actually just yesterday we talked about absolute value of x and how it's a piecewise function, how we can take it out of absolute value. We talked about absolute value of x is x when x is greater than or equal to 0 and negative x when x is smaller than 0. We talked about that. Why? Why can we're allowed to take it out of absolute value and use this? Because these two branches force it to be positive, right? If x is negative, I put it negative x in here, I got a negative times negative is a positive. It forces it to be positive. That's why I'm allowed to replace this with one of these branches. Okay, so now that's all pre-knowledge, things that we need to think about as we go to this. So what I'm going to be multiplying by here is the square root of 1 over x squared over 1 over absolute value of x. That's what I'm going to be multiplying by, and that kind of freaks students out. They're like, what? Let's talk about it. I know I'm allowed to square root things separately. I can square root the numerator separately from the denominator. The square root of 1 is 1. And the square root of x squared, I just established the square root of x squared is absolute value of x. That's what it is. These are equivalent. Why do I need both? Well, I've got a radical up here. I can't multiply an absolute value to a radical. That's not going to do anything to it at all. And I'm going to have to multiply a radical times a radical in order to have any effect whatsoever. Okay, so I'm going to use the radical. So these are equivalent. I hope we agree that the numerator is exactly the same as the denominator. It's in the different form. So when I have a radical, I'm going to use this form to multiply by. When I have a non-radical, I'm going to use this form to multiply by. Straightforward. That's it. So let's do that. Let's multiply it out. So I have the limit as x goes to negative infinity. And I'm going to multiply and simplify at the same time. So I'm going to take the 1 over x squared and multiply it inside there. Actually, I might, I won't simplify at the same time. This might be kind of confusing. I'm going to go ahead and multiply it out. So I have x squared over x squared plus 3x over x squared minus 1 over x squared. That's what I have in my numerator, because I multiplied by a square root of 1 over x squared. In the denominator, I'm going to have 3x over absolute value of x plus 1 over absolute value of x. Now before I go on, I'm going to do one more step and I'm going to simplify. Now simplifying, I can simplify under the radical. That's going to be an easy case. This is where it freaks students out. So I want you to think with me, because this was a really big problem earlier today. I'm going to negative infinity. My x's are negative. That's what they are. This is what it tells me. X is headed to negative infinity. I can't work with an absolute value. I need to work with the definition. So if my x's are all negative, which branch am I going to use to simplify absolute value of x, to take the absolute value bars off? I'm going to use this bottom branch, right? Okay, because I can't work with absolute value. I can't calculate with those. That's not a thing. So let's keep going. So I have the limit as x goes to negative infinity. So underneath the radical, I have the square root of 1, and then plus 3 over x, and then minus 1 over x squared. In the denominator, I have 3x over negative x plus 1 over negative x. Now, if my limit was going to positive infinity, would I be using negative x down here? No, I would be using this top branch, right? I'd be using positive x to simplify. Are we all clear on that? Okay. So now, let's take the limit. All right, so this little fraction right here is going to tend to 0. This little guy is going to 0. This is tending to 0. This I would simplify, right? X over x, that's just 1. So basically what I'm left with is the square root of 1 over negative 3, or negative 1/3 is my answer. And that's like the most complex kind we'll be dealing with for limits to infinity. Okay, questions on that? All right. So the last one is where we're just taking this integral and we're turning it into one of the formulas. I do not expect you to memorize the formulas. In fact, I'll just write them up here. So this is what, 1 over square root of a squared minus u squared du integral 1 over a squared plus u squared. Okay. So what our job is going to be is just to make this look like that. I mean, that's all. What do? Well, first of all, this constant that's on top, I just pull it outside. That's an okay thing to do. And I got my 1. Great. I'm pretty close. All right, pretty close. So the 7, I need to make it look like something squared. Well, how can I get 7 to look like something squared? Well, it would be square root of 7 squared. That would be, so I'm not allowed to change a value, right? So square root of 7 squared, of course this is all under radical, minus, now this is the part that confused students, which is why we're doing this, because this comes up next year, and it's this algebra part that people have trouble with, not that calculus part. So I need this expression to be u squared. I need it to be something squared. Okay, the whole thing needs to be something squared. I think we can agree that x is part of, that's very easy, right? X. What about the 2? 2, square root of 2, and I have to have a square root of 2. Square root of 2, because this whole thing is going to be squared. So we're asked to state a and u. A is the constant, a is the square root of 7. U is the square root of 2x. Okay, that's all. That's all we're doing here. Then we're stopping. There's nothing else. We're just getting it to look like that, and then we're stopping. Okay? The next one. So I'm going to pull the 5 out, 1 over. Pretty straightforward. This is the number. That's the a part. I need this to look like something squared. I think that one's pretty straightforward for us, right? That would be 2 squared. 2 squared. And I don't have to do anything to this. It's already x squared. So basically, a would be 2. And I mean, if you want to write u would be x, that's what it would be. But it's just, it's already in the form that we want it in. Yes?
Is there any reason that you only put 2 of those up there? I mean, I guess you just already know that there are 2
Yes, I know, right.
So we'll actually use the third one.
We will use all 3. Yes, so yeah, those are things that are just in my head that I just wrote the ones I knew we were going to need. I didn't write the third one. Uh-huh.
And is there a reason for B why A is only not the positive value? Or like, could you ever make it a negative 2 squared?
No, it has to be positive. Yeah, good question. No, it has to be positive. It can't be negative and work in this scenario. This number cannot be negative and work in this scenario. It has to be positive. Okay? Any other questions for me? All right.